let's start with some notation. So G is a finite abstract simplicial complex, a finite set of non-empty sets closed under the operation of taking finite non-empty subsets. So I have a couple of examples here of simplicial complexes. This is an example of a simplicial complex. Another example of a simplicial complex. So it has to contain all subsets. And for example, this is not a simplicial complex because it doesn't contain, this is a 3-point set and doesn't contain the, so you would have to close it, and that's the closure. So that's the smallest simplicial complex which contains that triangle. So there are open sets in this simplicial complex. There's a topology. It's a finite topology generated by base given by all and cubics, stars. So stars play really a very important role. This may be called that the reason why they're called stars, right? They look like that. They don't have the boundary. Right? This is also a star. This is a star of an edge. Actually, this is a star also. This is a star of a triangle itself. And so if you have a simplicial complex and then the facets, the maximal simplices, these are by themselves as an element are open sets. So this is a finite topology. And so once you have a finite topology, you can also use sheaf theoretical tools. So this is Alexandrov because they are smallest. These are the smallest open sets which contain a point. It's non-Hausdorff. So, and I also want to already define the characteristics. So we always use this notation. This is -1 to the dimension of x. And we also do that for a set. So if x is a set of sets like this, then we have omega x, capital X. This is small. It's just a product of the omega xk. So this is some notation we are using, and then we are defining these higher characteristics. So omega k, omega m of g. So this is the sum of all x g of m, where the intersection of all the x is equal to 1 to m is not empty. Then we take the omega x, the higher characteristic. Higher characteristic is a generalization of the Euler characteristic. So Euler characteristic. Very important notion. There are lots of interesting theorems. The most beautiful theorems in mathematics deal with Euler characteristic. It's a supercounting of a supercount, and this has then a property that it's very stable. It's stable under homotopies. Right? If you make a homotopy extension of a space, right, it doesn't change. You can do that even. It doesn't have to. It can be anything which you do which is homotopy transformations preserve Euler characteristics, but that's not true for the higher characteristics. So omega 2 already the Wu characteristic. So I worked on this a couple of years ago, and so they have a cohomology, they have a Euler work array formulas, etc. So they are very nice. But this is only invariant under homomorphism. This is not the homotopy invariant. It's a topological invariant. And it's very exciting because it allows you to distinguish spaces which you cannot distinguish with Euler characteristic of the cohomology, like a Möbius strip. A Möbius strip has a different Wu cohomology than a cylinder, so it's very, very powerful. Now, what is the thing? So we have also green functions. So if x, so now I take an arbitrary configuration of points. So think about them as k points, and then I define the GM x is x, and then this is Wm of u of x, where u of x is the intersection of all k equal to 1 to m, u of x k. So this is something I have kind of thought about quite a while with this, worked with these green functions, because they are interesting. They have interesting properties. So green functions, k point. Green functions for the nth characteristic. And so u of x, so these are all these neighborhoods, so it's really a topological notion. Because it involves the open sets u of xk. And so example, n is equal to 1, k is equal to 2. That's actually how the whole thing started. And then we have gxy. So x, y. And then we have Euler characteristic of ux intersected with u of y. So that's a matrix. N times n matrix if n is the number of elements in your complex, and G inverse is L, is the connection matrix, connection Laplacian. So that's how the whole thing started. I started with the observation that the connection Laplacian, and the connection Laplacian is an n times n matrix where Lxy is equal to 1 if the two simplicities intersect, and otherwise it's 0. And I noticed that this is always unimodular, the determinant is 1 or minus 1. So the inverse is an integer matrix. And then I wondered what the integer matrix entries are. And it took me a couple of months to figure that out. And because these are not simplicity complexes, these are open sets. Open sets are not simplicity complexes. Closed sets are simplicity complexes. So that's quite. So I was looking for simplicity complexes, formulas involving simplicity complexes, and I almost always worked, but not always. So there's a difference between open sets and closed sets. So this is a closed set. This is an open set. this is Euler characteristic 1, this is Euler characteristic 1 too, but if you take a one-dimensional, so this is Euler characteristic 1, this is Euler characteristic -1, this opens it. So you can also compute the Wu characteristic. And so this is the framework, and I want to formulate now the theorem. So, something I discovered this over the break. Main theorem is so we are giving M and N arbitrary. So this is the level of the energy level. So for example, M is equal to 1 is Euler characteristic, M is equal to 2 is Wu. And K is the particle number. So we look at K point green function entries, which means we are looking at the potential energy of a K point configuration. So this is X is in G of K. No assumption is here made about the intersections of this. They can in general be disjoint, but their open sets have to, and then we have omega X, and then we have omega M of U of X. This K point green functions. Well, maybe interesting for a physicist who thinks about, you have K particles. And let me just take an example, kind of in the case of M is equal to 1 and K is equal to 2. So that's the thing which I started with. What happens then? Then we have omega 1 G Euler characteristic is the sum x, y, arbitrary, omega x, omega y, and then we have the G1 x, y. So the sum over all green function entries. So this is what I call GMX. K point green function entries. So pretty cool. So already in the case K equal to 1, that's something I wrote about a little bit before. So if you take K equal to 1, for example, this is one point. Most physics deals with 2 point. You take green functions with two points, because physics of 3 points is already terribly hard. And so, but this is in general, so K points and the nth energy. So this involves kind of molecules of M simplices which all intersect. But this here you don't make this assumption that this is an arbitrary configuration of K points. So these are points, and then the G x1, x2, x3 potential energy free particle configuration. And you sum up all this energy, so this is the total energy. And this is the energy of a K particle configuration. Now, let's just say what happens when you take one point, and we have, it's actually pretty cool, because then we have x in g omega x, and then w m u of x. So the star, the energy of a star, like here this is the star of an edge. The energy of a star, this is the star of a point. The energy of a star here times wx, that's the green function, that's g of x, it's just one, this is g of x, this is the formula. And I also know this is true when you take the ball, not instead of the u, you take the ball. So let me just define this, so b of x. So this is the standard closure, topological closure, the smallest closed set, the intersection of all closed sets which contain a set. That's the closure. That's a simplicial complex, and then S of x, this is the boundary. So this is u of x, u of x minus u of x, this is the boundary. The ball, so this is the unit ball, and this is the boundary, this is unit sphere. For some very strange reasons, in simplicial complex language, this is called a link, but not always universally, so some only define it for vertices and not for, in general, for any simplex. This is the unit sphere is much more intuitive, because that's what it is. It is the closure of the unit ball, and at the boundary, it's the boundary of the unit ball. That's the sphere. Now we have also the same thing and the proof is the same, and then we have a local formula, so omega m bx, so omega m ux plus omega m sx. Now that's wrong in general for general closed sets as an interior and boundary. So, but that is a local valuation formula. That's very cool that we have still also for the higher energy we have this valuation formulas. There's also a general valuation formulas for open sets. It's opened my eyes. It's an eye opener to look at open sets. So it looks like a small thing, but it's really, really kind of changes the whole thing. Because what happens, for example, you have a omega m u union v is u plus minus, which is true for Euler characteristic for arbitrary sets, but for in the higher characteristic it's wrong for arbitrary sets, but it's true for open sets. That's very cool. And this is the local valuation. This is the valuation for open sets. And then you subtract them. You subtract these two things, and then you get the 0 is sum x in g omega x omega m sx. And I call this the sphere formula. I made a big kind of a bit of splash with that, writing a whole article about this, because it looks kind of like an innocent little thing, but it's quite important, because if the omega m of s of x is equal to is constant, like for a manifold, This is an example of a manifold. A manifold is a simplicial complex where every unit sphere is a sphere. And the sphere is a manifold, so that when you take a point away like this, is actually a sphere also. If you take a point away, or an open set away, you take an open set, you take the star of a point away, then you get still a closed set, because you have subtracted an open set, then you get a closed set, and this should be contractible. And contractible is defined inductively. It's contractible if you can take an open set away, so that it's contractible. You can take an open set away, so with a contractible unit sphere, so that it's contractible. You can take an open set away with a contractible unit, with a contractible unit sphere. You see, that's the unit sphere here. And then you can take an open set away, so that you have, and then you're stuck with a 1 point, and you declare the 1 point. Simplicity complex 1, you declare to be contractible. The empty complex is also a simplicity complex. That's a minus 1 dimensional sphere. And the 2 point complex with no, this is a 0 dimensional complex. You take 1 away, so you can take that away. It's an open set, and you remain with a contractible. It's pretty cool that you can formulate everything within finite sets in a very, very intuitive way. And so what happens is, because this is 0, so for manifolds we have actually then, maybe I just write that here, manifolds. I think I defined what a manifold is already about 10 times in these videos. So for manifolds, the WMG is W1G. So manifold, I always mean a closed manifold, no boundary. For boundaries, it's also interesting. I will come to this maybe next time. It's quite interesting story. Let me wrap this up without actually making another. I hope I will kind of have that a draft ready soon. But the proof I have sketched a couple of times already, also last December, and so the proof is actually quite simple. And what you do is you realize, just in order to prove this, you realize that you can actually define this Wm, this energy, you can define much more generally. So what you do, maybe I just still kind of say something about the proof. So something about the proof. So first of all, the whole thing is much more general. So what we can do to define Wm, we have a function h from g to the m to r, and this is some ring. So the whole thing fits very well into sheaf theoretical frameworks because we have a topological space. We can attach to every open set, we can attach for every open set we can attach a ring. Especially for every x. And then you have just to say how you and then this is actually this is the stock. And the elements in this stock are the germs. So everything is finite. We have finite objects. We don't have to do any limits. So everything is very, very concrete. And for example, you could take maybe, let's take z, the integers. And so what you have is then, when you have this function given, what we have is then you define h, is the sum. all these molecules which don't intersect, what you take is you take just h of x1. So this generalizes the setup where h of x1 and xm is the product these plus or minus 1 cases. So this is actually we don't even need the ring structure. You can work with groups, and you can additive groups and everything. But usually the framework in sheaf theoretical frameworks is you work with local rings or local ringed spaces. So that's the thing. And then what we have is then so we have then the G MH. G is defined the same way, right? So this is so X. So this is for so this is G X1 and G Xk. This is a function of k variables, and that's then just defined as the omega of x. That's the same omega, we don't change that, so this is plus minus 1, and then we take mh u of x. So everything is just, you know, generalized. We have arbitrary functions of m variables here. And now, so this map, which maps H goes to G, is linear. And the energies are all linear. So this is a linear framework, linear algebra framework. And so what you only have to verify, we only have to verify it for very basic functions. And 1x is equal to z. So just take one molecule, right? You take one molecule, x1 and 2xm, so set of simplices which all have a common intersection, and you take the value 1 there, and everywhere else you have 0, and then you verify the green function identity in that case, and then by linearity it holds in general. So all the other characteristics, all the higher characteristics of manifolds are, they don't give you anything new, but the homology gives you something new. So this, we will come to this hopefully in this semester. At one point I want to talk about the homology more, which is really interesting. So that's what I wanted to say. Let's finish this.